I would like to proceed into the lecture, into the brief lecture. So I'll just share my slides, and I request everyone to keep their microphones off as requested by the organizer. So I hope you can see the slides on the screen.
Yeah, it's visible.
Okay. Okay. Yeah.
Yes, you can.
Yeah. Okay. So first of all, I welcome you all to this webinar on emerging semiconductor devices, trends, and challenges. And I thank the organizers of HBTU Kanpur. And this is under the banner of IEEE, as I have come to know. And as already introduced by Dr. Saha, I belong to the Department of Electronics and Communication Engineering, Tejpur University. So let's move into the topics. Before proceeding into the topics, there's very interesting about today's date, the 28th of May 2020. And the interesting point is Alan Turing, he filed his first paper, or he published his first work titled on computable numbers, based on which you see the today's computers and the machines. So it was done in around 1936. So that is quite an interesting fact I came across, and I thought of sharing with you all before moving into the lecture. So let's proceed. The key contents of today's webinar will be the ones which you see on the screen. I call them key contents because apart from these, we will be discussing some other aspects also. And to begin with, we have already studied, and I assume that everyone is, all the students are so acquainted with MOSFETs, and they have basic ideas of the Moore's law. So we will not spend much time on the, understanding the operating principle and everything, and we'll just discuss a few stories and move into the emerging devices. So I have selected three emerging devices for this webinar. The tunnel field effect transistors, the fin-shaped field effect transistors, and memristors. And these are like the missing links which people are trying to dig out so that we can go beyond the Moore's law. And apart from that, we will also look into some biosensing applications and discuss the prospects in these specific applications. And also we will discuss some philosophical objectives of doing research towards the conclusion. I know that this 2 hour is not sufficient to cover such a very broad topic, but I'll try to graze along the important points through the webinar. And I just want you to enjoy the webinar instead of just taking it like a course or a study-oriented program. So I want you to enjoy the facts which I'll be sharing, and we'll just try to keep this as simple as possible. So before moving into the key contents, so let us watch the world's smallest movie. So this particular movie was built by IBM, and it holds the Guinness World Record for the world's smallest stop-motion film, and it has been done using the scanning microscope, and the movie is being made by moving atoms of carbon. And so just let's see what this movie is all about. So I hope the YouTube screen is visible. So please, someone please respond if.
Yes, yes, it's visible.
Okay. So we are back on to continue with the lecture. The reason why I have shown this, I hope the screen is visible, the lecture is visible, right?
Yes, yes, it is visible.
Okay. That was the world's smallest stop motion film. And the reason why I have shown this, because we are going to discuss about the scaling trends also as we move into the nanoscale domains and into the atomic scale. So this is what IBM is doing on their part. So it is actually an old video, but this is the trend which is going to be set in the future for atomic level processes and transistors. So by moving the atoms, what you can do is you can also change their states for attributing logic values to that particular transistors. So although we will not be taking this particular atomic level transistors, but I felt that you will enjoy this video. So let's now move into the key contents of the lecture. The first point, the MOSFET versus Moore's law. Uh, the discovery of field effect in devices. So every one of us know that the MOSFETs are one of the very key components in design of our integrated circuits. But there are very interesting stories of the discovery of field effect. And most of you must be knowing, but still I thought it would be better to share this information. So, in fact, in 1947 and towards the end of 1947 and the beginning of 1948, the team of Shockley, Burdeen, and Brittain, they were working on the point contact transistor and the junction transistor, which we also know as the bipolar junction transistor. And during this period, they tried to look for the field effect phenomenon in their devices, the point contact transistor and the junction transistor. And they filed patents on both these devices. But unfortunately, the patent office rejected 65 of their claims because of one particular person, Julius Lilienfeld, who had already filed a patent on field effect in his patent title Device for Controlling Electric Current in 1928, which was way before the invention of the junction transistor. So this is the Lilienfeld's patent drawing, which you can see on the right-hand side of the screen. And the reason, the most important point why I thought of bringing this up is because whenever we study electronic devices, we try to go through the concepts and the various architectures, and we get just tangled up in the process, and we get so confused sometimes, particularly the students and the researchers. Even I felt such demotivation while searching for problem statements during my research time. And but the more interesting it gets when you try to understand the historical significance of that particular device, and to see how imagination had already crossed barriers even it came into existence. So while going through the concepts in the textbooks and the research papers, so it is always more interesting, and things become easier and convenient when you try to dig out some of the historical significance of those particular works. So that is the reason why I have brought this up. And interestingly, the name of Lilienfeld only appeared when Shockley, Burdine, and Brattain went for the patent for the junction transistor and the point contact transistor. Now coming to MOSFETs,
Audio is not there.
This is not audible.
is the audio clear now?
Now it is.
Previous slide, audio is
Now
not
it is-
there. Audio.
Is it clear now?
It is
Now
clear.
it's clear.
Yes, yes, it's clear.
Rupam sir, just turn off your video. I think it will save the bandwidth.
Dr. Suman, audio, video both were clear here.
Yes, sir. I am trying to contact you.
No,
I think by mistake he has logged out. So maybe he will log in again.
okay.
Correct number dial again.
Am I audible now?
Yeah.
Yes,
Audible.
yes, you are audible. What's going on?
Hello?
Yeah, we
Yeah.
can listen to you.
Yeah.
Yes, present now.
It is clear, right?
Presentation is not coming.
Just a minute. Is it coming now?
No, not
No.
till now. Yeah, it is.
It's coming. Wait.
Yeah,
Okay.
it is okay.
Wait.
So we'll start from this slide, right?
I think
Yeah.
previous slide.
Okay. So just a minute. So we'll start from the previous slide or this slide?
I think this slide. Show the content. I think this slide onwards.
This slide? Okay. So we were discussing about the discovery of we had already, I had already Shockley, Burdine, and Brattain, Julius Lilienfeld had already. What you see on the right-hand side of your screen is a snapshot of Lilienfeld's patent at the US Patent Office, probably. And so it becomes very interesting when you try to understand the historical significance behind a device while going through the different concepts and the topics which you see. Okay, so let's move to the next slide. I hope I am audible to all of you.
Yeah, yeah.
Yes,
Yeah.
audible, audible.
So next, all of us have almost seen a MOSFET in our textbooks, particularly the 2D schematic of the enhancement mode and the depletion mode, N-type and P-type MOSFETs, right? But there is another question which we normally do not encounter, which is who invented MOSFETs? So there is another story behind the invention of MOSFETs. So in 1956, when the BJTs were becoming saturated due to their surface passivation problems, so the Bell Laboratories, they gave Atala and Kang to work on the passivation problems. And during this period, they built the insulated gate field effect transistor, which is a version of the modern day MOSFETs. But unfortunately, their work never got a wide recognition because of the corporate matters and the legal issues with the laboratories, and they remained in the official papers of the laboratories itself. In 1962, F.P. Hyman and S.R. Hofstein built another version of the silicon ICFET, or the insulated gate field effect transistor, and this particular device is considered to be one of the most significant ones in line with the invention of MOSFETs. So at the bottom of the slide, you can see the reference which discusses such inventions and histories on the MOSFETs. Okay. So now we'll proceed to the Moore's law, the famous Moore's law, which actually was a prediction. It became a law only in 1975. So when Gordon E. Moore first looked into 3 dataset points for Fairchild Semiconductor and 2 other semiconductor companies, so he predicted that the number of components per chip would double every 2 years. Okay. Interestingly, he deduced this just from a set of only 3 data points. So this shows how eager he was to expand the semiconductor industry. And after that, however, he realized that the doubling would occur every 18 months instead of 24 months. And thus, he gave the second version of his prediction, which is now, which was later known as the Moore's law. Okay, so what you see on the screen are some of the data set points collected from his appearance, or the first paper titled Cramming More Components onto Integrated Circuits. So that was the first time G.E. Moore gave the idea of this prediction, okay, in 1965. And later on in 1972 or 1974, he modified his law according to the evolution of the number of transistors. So what he wrote in his paper is written highlighted in yellow, which says that the complexity for minimum component costs has increased at a rate of roughly a factor of 2 per year. So certainly over the short term, this rate can be expected to continue, if not to rise. So this was what he gave as a prediction in his first article in Electronics in 1965. And this is an excerpt from The Economist, April 19, 2015. So you must be wondering that instead of discussing the Dennard scaling law and everything, we are just sticking on to Moore's law in this webinar. The reason is because whatever we are doing today in the research perspectives or the domains, everything comes from the prediction made by Mr. Moore way back in 1965 to 1972. And everything is related to the economy and the market rather than just low power applications and applications in mobile phones. So the Moore's law is actually not limited to the semiconductor industry. It encompasses the whole world of economics, because the semiconductor industry has a major share in the global economic forums. Okay, so this is what appeared in The Economist in April 19, 2015, and you can see that it was reported that when transistors 28 nanometer wide were the state of the art, chip makers found their design and manufacturing costs beginning to rise sharply. So as you shrink your device, so you must also be careful about the costs which you are bringing along with them. So therefore, this excerpt is very much true. And while dealing with devices, although we try to shrink the devices in our simulation perspectives and also in our modeling perspectives, but those are only with reference to what we will do in the future. So therefore, the importance of Moore's law goes in and around the semiconductor industry and into the economics of the world. So another common term, or say a society, you can say, the ITRS, International Technology Roadmap for Semiconductors. So this was formed with the objective of making predictions for some future years for various electronic parameters, and also for different applications and for like high performance, low power applications and other things. And also they tried to give the emerging devices which can be very significant in the coming years, right? So until 2015, the ITRS was known as ITRS, but after that, from 2016 onward, now it is known as IRDS, the International Roadmap for Devices and Systems. And this currently comes under IEEE. So IEEE now holds the IRDS documents, which you can download if you have an IEEE membership. So if you see on the left hand side of the screen, this is what appears in IRDS 2018 edition. So this was the last edition which appeared, and you can see these are a list of different emerging devices. So this can also be your research topic if you are finding something to work on. And they have been categorized along the horizontal axis into conventional and novel, and along the vertical axis into charged and non-charged based devices. So this particular thing, the figure 1.3 which you see, is important from the perspective of future devices or emerging trends, and also on the shrinking of dimensions. And what you see in figure 1.4 is a colorful roadmap which got published in ITRS 2013, which speaks about different devices which can be in research and which have prospects based on the years. So what you see at the top on the screen here along the years are, so it goes from 2013 to 2028, and these colors give the requirement for research required or development underway for blue, qualification or pre-production for pink, and continuous improvement for yellow. So for example, if we pick up tunnel FET or the tunnel field effect transistor, which we will discuss today, so you will find that it is predicted to be under research up to 2022. And from there on, there will be development of that particular device. So this is a prediction which got appeared in ITRS 2013. Okay. So now we will move into the novel devices which we are thinking of taking up in this webinar. But before that, so first the question is, why are we moving into these novel devices or these emerging devices? The, the prime concern is the degradation of performance of the MOSFETs when they are shrunk below certain dimensions, and these are nothing but the short channel effects in MOSFETs. So we will not just will not discuss this in detail. Just a very brief outline of why we are moving into this. So whenever you are shrinking the gate length of a particular MOSFET, so you will find that the source and drain regions will come very close to each other. Okay, so if you see this picture on your screen, so once you shorten the gate length, so the source and drain regions will be close by, as a result of which there will be charge sharing between the gate and the drain. Okay, because you have a very lightly doped p-type substrate and a heavily doped n-type drain here. So most of the depletion region will exist towards your substrate. So this is basic p-n junction, which says that higher the doping, so lesser will be the depletion width. So in this case, the n plus drain is having a very high doping, so you'll be having a very less width of depletion region here, and most of the depletion region will be towards the p-type substrate. So now when you are bringing this closer, the drain, the electric field emanating from the drain can now control some of the charges in your channel. So the gate is actually losing control. So it is like you have a switch shop in a particular area, and you are the owner of that particular shop. Now someone comes to you and says that I'll be taking this shop on lease for say 20 years. So you don't have a problem usually if he takes only a very small share of your sweets or your profit. Say he takes only 2% of your profit, so you don't have any problem. But if he tries to take over around 90% or say 50% of your profit, so that becomes a problem to you. So this person who has come for the lease is the drain we are talking about, and you actually are the gate. So you were controlling the switch shop business, and now you find someone else coming and taking your profit. So the short channel effects can be very well explained with this example. So whenever you are shrinking the dimensions, the control of the drain over the channel increases, which we do not want. It is an unwanted effect. We want the gate to control the channel. So therefore, for short channel effects, it becomes a very big problem. And therefore, in MOSFETs, people have seen that the reason for this is the principle of operation of these MOSFETs. So therefore, they have tried to get around this problem by trying to develop devices which can somehow increase the gate control or have a principle of operation which is different from the thermionic emission principle in MOSFETs. Okay, so I hope you have just got a basic idea. I do not want to stress on the different short channel effects, but I just wanted you to give an idea of why we are doing this, why we are doing this webinar. So now moving into the novel devices. So first of all, the term novel is not absolute term, it is a relative term. So when we pass and go into the future, this novelty of these devices will decrease. So this is novel only with respect to the present we are talking about. Okay, so the first one is the tunnel field effect transistor, or popularly known as the TFETs, and this has emerged because of its difference in principle of operation with MOSFETs. Okay, so basically the tunnel field effect transistor is a gated reverse biased PIN structure, or you can say if you have a tunnel diode and you put a gate over the intrinsic region. Okay, so in that case you get the architecture of a conventional TFET. So it works on interband tunneling or band-to-band tunneling. And Jenner tunneling is the primary principle of operation, and it has two modes of operation: the bipolar. So it is a bipolar device, the p and n channel modes, depending on the bias which you apply to its terminals. So in this webinar, we will be restricting our discussions to the n-type TFET only. So on the right-hand side in figure 3.2, you can see the energy band diagrams of TFET, which we had simulated on the Santera's TCAD platform. And so you can see there are two energy bands. One is for the 0 volt, which is the off state, which is considered to be the off state for the device, and the other is 1.5 volts. So these are gate voltages, and the drain voltage is kept fixed at 0.5 volt with respect to the source terminal. So once you start applying the gate voltage, you will find that your bands will be suppressed, as a result of which you can have a tunneling window created at the source channel tunnel junction. So it is called the tunnel junction because it helps, or it creates the opportunity for tunneling of carriers from source to channel. Also, another important point which you need to see is that from the source, the minority carriers are tunneling into the channel because the source is p-type. So this tunneling process depends on a number of factors, which we will discuss in one of the upcoming slides. But before that, once again, let us see some of the interesting facts about the invention of the tunnel FETs. So just like MOSFETs, even for TFETs, it was proposed by Schweitzer in 1952, way before the invention of the Saki p-n tunnel diodes. Okay, so Schweitzer proposed this particular device, and he called it the junction filters. So he rarely used the topic of tunneling, and he used a p-n junction to demonstrate the effect of position of gate over the junction. So what he did, you have a p-n junction and you place a gate over that, so it can act as a very well maintained field effect device. And the main reason through which it operates is the band-to-band tunneling. So it is similar to your Jenner tunneling in your p-n junctions, but a placement of the gate over the junction creates more possibility of tunneling of carriers. So you see the header of the proceedings of the IRE in which OM Schweitzer published, and a snapshot of the uncased device, which you can see it has 3 terminals, as you can see in the lower figure which is shown. And this is a schematic of the p-n junction filter which we proposed in his paper or article. Okay, so so we can see that just like MOSFETs, the concept of TFETs actually evolved way before even the invention of MOSFETs in 1960s. So this is quite interesting, considering the fact that we are doing rigorous research on tunnel FETs towards the 2000s, after the 2000, and continuing up to now, right? So this slide shows an animation of the operation of conventional TFET. Okay, so what you see is the bending of bands and the creation of the tunnel window when the front gate voltage increases. So the front gate voltage is actually the gate voltage we are talking about, because there is a single gate. So in case you had a double gate, so then the front and the back gate voltages would matter, the terms. So here we have a single gate, and on application of the voltage, so these bands will bend, and it creates a very good tunneling window for carriers to tunnel through the barrier. Okay, so this animation gives a brief idea of the principle of operation of tunnel field effect transistors. Now, the most important thing while doing any device on tunneling, specifically the band-to-band tunneling, is the tunneling probability. So this term actually comes or stems from the quantum mechanics of devices. And in this case, we normally treat the energy band diagram as a barrier and then calculate the tunneling probability. Okay, so this expression which you see on the screen is a very popular expression derived by WKB. It is known as the WKB approximation for tunneling probability, and it can be used for TFETs, and it has been used for TFETs considering the fact that you can have a triangular barrier. And if you consider a triangular barrier, so you will find that the tunneling probability will appear something like this, what you see on the right hand side of the expression. So this particular expression on the right hand side of the arrow is actually the expression for general expression for tunneling probability in any tunneling device or TFETs. Okay, so you can see that the lambda is the tunnel width, the Eg is the band gap of the semiconductor at the tunnel junction. So you must be very specific about this, because you can have a different material at the tunnel junction in order to modulate the bands in and around the junction. Okay, and the delta phi is the overlap of valence band and conduction band in source and destination, and Q is the elementary charge, and M star is the effective mass, and H cut is the reduced Planck's constant. But what is more important here is the terms, the band gap of this particular junction, the tunnel junction. And you can see on the screen that if the band, if you are applying a gate voltage, the bands get suppressed. And as you can see, the scope of tunneling of a carrier to tunnel through this window will depend on the band gap, because if you consider a tunneling barrier of triangular nature, so you will have a possibility to tunnel into all the directions starting from that point. Although this is a one-dimensional case we are considering for the expression, but if the energy band gap is small, so the carriers will have more probability to tunnel. It will require less energy to cross the barrier. So this is one of the key aspects why people go for heterojunction devices, and they use mole fraction dependent semiconductor materials like silicon germanium, and they try to modulate the band gap and other properties. And the silicon germanium also becomes very advantageous because they belong to the same group as silicon, and this also facilitates in the fabrication processes. So the tunneling probability is one of the key parameters of understanding TFETs from the quantum mechanics perspective. Okay, and there is another term, the term which we have been using, the band-to-band tunneling rate, or the band-to-band tunneling. So this is a specific expression for the band-to-band tunneling rate in a TFET. So here you can see on the right hand side, we'll discuss the different parameters here. So A and B are actually material constants, and they can vary from one material to another. So these are actually, they can be called empirical constants with respect to a new material discovered. And E is the electric field, which is the net electric field across the device. So if you are taking a two-dimensional case, it is root over EX square plus EY square. And if you're taking a three-dimensional case, so accordingly the net electric field formulation will change. And EG is the band gap, as we have already seen in the expression for tunneling probability. And you can see that the tunneling usually occurs at exactly the junction between the source and the channel. So in this particular case, the structure which we have simulated has a gate drain underlap. So gate drain underlap is that the gate has some distance away from the drain junction. So this is the gate drain underlap, and you can see the source is a bit extended inside. So you will have this particular tunneling rate at delta P plus and channel junction. And you can see the rates are marked here in color in the diagram below. and the maximum has been given for the red color. And as shown, you will have maximum tunneling rate close to the surface and near to the junction, because close to the surface you will be having the maximum impact of the gate, and close to the junction you will be having the steepest gradient in your energy band diagram, as we have seen in the principle of operation here. So, and the on state, you can see the steepness increases, and that is what we require, what is required for your tunnel FETs to operate. So therefore, the band-to-band generation rate is located or centered around this particular junction near the interface of the oxide and semiconductor. Okay, so now in this case, one thing which I would like to discuss, a brief discussion on what is the outline of arriving at this band-to-band tunneling rate. So people who, most of you who are doing research on this area will be very much acquainted with this process, but still I just like to have a brief discussion on this, so that the other students also get benefited from what we are trying to do here from the perspective of analytical modeling. So at this point, what becomes more important for us is to distinguish between simulation and modeling, and learning how to use experimental evidence to calibrate your simulators and different models which we are using. So basically, if you see into the picture, and it is very evident that the simulation perspective is basically done on a numerical kind of simulator, through which you get more accuracy depending on the different parameters which you can tune, and the analytical model which you specifically derive. So in a very layman sense, it is a mathematical derivation of the different parameters which you can do using your notebooks. So in the analytical model, we try to go step by step, starting from the Poisson's equation and trying to incorporate the different conditions, the boundary conditions, and the geometrical dimensions, right? So in this case, you will see we start with the Poisson equation. Now we are discussing how to arrive at this band-to-band generation rate through mathematical derivation, which is a pretty interesting work if you take up. So this is the Poisson equation. From that, we can derive the potential profile for this device, applying the different boundary conditions and approximations. And from there, we can have the electric field profile, because once we have the potential, you can take a negative gradient and find out the electric field across the device. And from there, you can get the BT-BT rate, because if you can see, the BT-BT rate expression depends on this E, which is the electric field. So this is where the BT-BT rate lies in your flow chart for TFETs when you are doing a derivation to understand. And finally, we have the drain current. And here, one thing which I would like to express from the different experiences I had, the little experiences which I had during the submission of different articles and doing research on this area. So prior to 2010 or say 2015, around this time, if you could derive a model up to the electric field or the BT-BT, say for example, so it was self-sufficient and considered to be better in case of doing your in case of obtaining the research objectives. But after 2010 and 12 or say 15 at max, this drain current derivation became very important. So now most of the students, they ask this question. So the question is something like this: we have the potential profile, we have the electric field profile. So obviously anyone having the equations can directly jump to the drain current. So we do not need to derive them. So that is one of the very common questions which we normally encounter during the research seminars. But the point here is not the accuracy of your potential profile or your electric field profile, The point here is what you are contributing to the research domain. The contribution will be very much significant when you give a closed form expression of the drain current. Now the question here, the question which occurs or appears in most of the students is why? The answer is, if you have a closed form expression, you can directly apply it to the circuit simulators. So imagine you have a circuit simulator and you are trying to incorporate a novel device, something which is not present in their libraries. So instead of doing a whole set of numerical simulations for the device and then going for the circuit simulator, what if you have a simple equation which you can directly plug in into your circuit simulator and then obtain the different results? So that is the beauty of analytical modeling, and that is where these questions become very significant. And it is not whether the potential profile or the electric field profile is sufficient or accurate. The question is whether you are able to derive the drain current equation for your device. So along with this particular slide, this information can be quite handy for researchers who are working not from the perspective of any mathematical expressions, but from the perspective of philosophy of doing the research. So these are some of the geometries of TFETs. And as you can see, the first one on the top left is your double gate TFET. And the advantage of the double gate is that you can control the channel from both the directions, and this gives a better tunneling window. On the right hand side, next to the double gate TFET, you see the double gate dual dielectric TFET. So in this case, what the objective is, you see there are two colors for the gate oxide here, blue and yellow. So we try to give a higher dielectric constant towards the tunnel junction and try to suppress the tunneling in the channel drain junction. So we will understand why we try to suppress the tunneling in the channel drain junction in one of the upcoming slides. Also, you have the gate drain underlap TFET here. Now, what is the reason for doing an underlap in a TFET? So the device is quite beautiful with the full gate over the entire channel. So apparently there appears no necessity of doing an underlap. But this underlap will eliminate one of the problems in TFETs, which is M bipolarity. And this M bipolarity, or the M bipolar current, is the leakage current or the current which is available when you are not operating your TFET in the operating regime. So for example, you are operating your device, say you are using it in a complementary MOS architecture or configuration. So you have the P-type TFET and the N-type TFET. So now when you are putting a negative voltage to your TFET to the CMOS configuration, the N-type TFET is expected to remain switched off. But you will see that if you are keeping the gate over the entire channel, you will find some leakage and there will be significant amount of current even when the P-type TFET is switched on. So this causes a very greater problem in digital circuits. So therefore, in order to eliminate this disadvantage, we introduce this underlap. So what this underlap does, it reduces the interaction or the influence of the gate on the channel drain junction, as a result of which you do not have much tunneling occurring in this area. So for an N-type TFET, the M bipolar current will flow whenever your gate voltage is negative, and for the better operation or the actual operation, the N-type operation will occur when your gate voltage is positive or greater than 0. Also, to put out at this point, the current which flows in your TFET during its on state occurs in the source channel tunnel junction, or the junction of the P plus source and the intrinsic channel, and the M bipolar current flows at the junction between the intrinsic channel and the drain type junction. So these are some of the key points why we introduce such changes in architectures. And going from the gate drain underlap TFET, we now move to the heterojunction TFET. So in the heterojunction TFET, you can see there's a green layer put just after the p-type region. So this green layer can be any material which has a lower band gap, just like germanium or silicon germanium. So in that case, once you put or incorporate a lower band gap material at the tunnel junction, so your tunneling probability will increase, as a result of which you will get higher currents. Okay. And these are some of the few, again, architectures, one of them being the silicon germanium source TFET. So instead of putting this layer of silicon germanium here just after the p-type source, which may cause some problems or inconvenience in your fabrication, so what you do, you start with a p-type source, which is wider in dimensions, and then you can fabricate this TFET, which will again give you a very higher tunneling probability, which is expected to give you higher tunneling probability because of the modulation of the band gap due to the silicon germanium source. Another device architecture of TFET, which was briefly appeared midway, was this wedge gate TFET. So the idea of putting a wedge here was to increase the tunneling area of the gate. So once you increase the tunneling area, so you will find that more amount of the area will be influenced by the tunneling rates, as a result of which you can expect to have higher currents. And finally, at the bottom, you can see circular gate TFET. So this was one of the architectures which I proposed, and this architecture is based on some of the patents done, or the US patents which have been developed. We had proposed a fabrication flow for this one also in one of the articles. So this particular circular gate TFET is advantageous because here we can modulate the radius of this particular gate. So you can see, if I decrease the radius here, so I will get two advantages at the same time. The first one being my dielectric oxide, my dielectric thickness near to the tunnel junction will reduce, and at the same time my gate drain underlap will increase. So as a result of this, we can have a higher current, tunneling current flowing through this device. So these are some of the architectures, and I have already put up that the list is not exhaustive. We are moving towards new dimensions and new proposals of tunnel field effect transistors in case of their architectures. And this list is not exhaustive, but these are some of the significant architectures which we can discuss in case of TFETs. So next, coming to the transfer characteristics in TFETs. So let's try to see what the parameters are while understanding this transfer characteristics. So you see this ID-VGS curve on the left, which we tried to simulate for and a constant of 22, which corresponds to the HFO2 dielectric. And the VDS is kept at 0.5 volt, and we have changed the bias, gate bias, from -1 to +1 volts. So as you can see, to the left hand side of 0 volts, or in the negative gate voltage regime, we can see there is significant current, bipolar current, which you can see there. And this is quite detrimental to your device performance. So therefore, we introduce the gate drain underlap and this dual dielectric concept. So towards the channel drain junction, we put a very low K dielectric, gate dielectric like SiO2, and towards the source channel junction, where the tunneling is very much required, we put a high K dielectric material. And this ambipolar current occurs towards the channel drain junction, and the current to the left of your 0 volts or towards the positive regime occurs at the source channel junction. So there are two junctions in a TFET, in a conventional TFET, and we can have tunneling in both the junctions, but we need, or only the tunneling in one of the junctions is necessary for us, and the other junction tunneling is unwanted tunneling, which we do not require. So we change our architectures with respect to that. Another point is that the MOSFETs have a limit to their subthreshold swing, and this is because of the thermal voltage limit of 60 millivolt per decade. But in TFETs, you usually can have lower subthreshold swings, and people and researchers have reported lower subthreshold swings in the range of 50 millivolt per decade or 30 millivolt per decade. And some of them, in case of 3-5 semiconductors like InGas, have also reported even lower subthreshold swings. Okay, so these are some of the key points. And on the right hand side, you see the transfer characteristics for a fabricated TFET, which was fabricated by Choi et al. In 2007. And the characteristics are quite wonderful, in the sense that it has a very less subthreshold swing, and also the gate length was reduced to 70 nanometers. So this is another advantage for your TFETs, is that the usual short channel effects which you encounter in MOSFETs are normally or ideally absent in TFETs. So the reason for this is, can be explained with the help of this diagram of the band-to-band tunneling rate here. So if you see here, you can notice that this red portion near the tunnel junction has an order of 10 to the power 29 of band-to-band generation. Okay, and the next yellow portion is around the range of 10 to the power 20 to 21. So it has a change of orders of like it changes by around 7 to 8 orders of magnitude. So what do we conclude from this? We conclude that this red portion, or the maximum tunneling which is happening, is confined only at a very small area in the junction. So even if we reduce the gate length, even if we are trying to reduce the gate length, that is not going to impact the on current of the device until and unless you try to do conflicts with that small tunneling area of that particular device. So this is the reason why you can scale down the gate lengths of TFETs without taking much precautions into account, precautions in the sense as compared to MOSFETs. Okay, so these are some of the key points of these tunnel field effect transistors, and we have discussed its disadvantages. The M bipolar current is the disadvantage, and another disadvantage which most of you must have noticed by now is the maximum on current. So for a MOSFET, you can have a maximum on current or in the order of 10 to the power minus 3, and here you can see it is just touching 10 to the power minus 5. Okay, so this is one of the concerns, and the reason again is the same, that it operates by tunneling and the entire geometry is reverse biased. So the PIN is reverse biased because you are putting a positive potential to the drain, and while you are keeping the source at ground or at the lower potential. So that is the reason why lower currents, and people therefore have gone to greater extents in modifying the architecture and the materials of constitution of these devices so as to improve the on current. But the advantages are the lower subthreshold swing and the lower leakage current, the I off, which you can see on the screen at 0 volts. Next, we will be moving into the FinFETs. And FinFETs are more popular than TFETs because they are already implemented in most of your mobile phones by companies like Xiaomi and Samsung, and they have already dived into the 7 nanometer regime at present. They're experimenting, and for the 14 nanometer FinFETs came and became a very popular term when Xiaomi used them in their mobile phones and in their processors. So we'll be discussing FinFETs next. And FinFETs are actually very interesting versions of MOSFETs. The conversion of MOSFET to FinFET gives a wide range of advantages which people had not thought of earlier. Okay, so basically in a planar MOSFET, as you can see in your on your screen in figure 4.1a, you have a planar MOSFET where the gate is just exists above the channel. And in figure B, you can see that the silicon has been converted into a fin, and the fin is now surrounded by the gate on all three sides. So the advantage here is, remember what we discussed a few minutes earlier, that in short channel MOSFETs, the control of the drain increases over the channel, as a result of which we have higher leakage current and lower threshold voltages and all the degradation in performance for MOSFETs. But whenever we are translating the entire channel into a fin-shaped structure, so now the gate can have a very better control over over the carriers in the channel, as a result of which you are now able to control the leakage current. You are able to significantly reduce the leakage current in these devices, and by modulating the dielectric thickness, you now have the opportunity of modulating the gate on three sides. So for example, with a gate with a different work function on one side and with another different work function on the other side, to just modulate the carriers in your fin-shaped field effect transistors. So in a very layman sense, it gives you the degrees of freedom to explore so that you have more control over your fin-shaped channel. So I hope the sound is audible.
Yes, sir.
Yes, it is audible.
Yeah. Okay.
Yeah, audible.
So now we'll just
Audible, audible.
yeah.
Yeah, audible, perfectly audible.
Okay. Thank you. Yeah. So this FinFETs, these have a wide variation of classifications. So I have just selected some of them, the most popularly used ones, which are also not just classifications. These are also different, you can say, architectures of this fin-shaped field effect transistors. So you have the short gate and the independent gate FinFETs. So the short gate is where you have a single gate over the entire which means the gate 1 and gate 2 materials are the same, and you just need to apply a single gate voltage to that particular terminal. And in independent gate FinFETs, as the name suggests, the gate 1 and gate 2 must be independently controlled, which means you can apply a different voltage to gate 1 and a different bias to gate 2. So there are advantages and disadvantages, and those are pretty apparent in nature. For example, in the short gate, you can just do away with one supply voltage, but for the independent gate FinFETs, although you can improve the performance by some orders, but you are also increasing the cost of adding another power supply for controlling the gates. On the right hand side in figure 4.3, you see the symmetric gate and the asymmetric gate FinFETs. So these are almost analogous to what you have seen in figure 4.2, except that both are kind of tri-gate FinFETs. So you see the gate is extended over all the three sides of the fin. So in this case, you have a single work function. Say you have a gate work function of 4.4 electron volt to control the entire channel. But here you can have the choice of employing two different work functions, but with a single supply voltage. So this now occurs on the material step itself. So if you want your device to be perfectly modulated, and you are very confident that inclusion of two different work functions can give you the opportunity to explore more current in these devices. So you can use the asymmetric gate FinFETs. But the point here is, once you change the work functions of the different materials, there will be some other complications which you need to take care of. First of all, the reliability of the material and the interface between gate 1 and gate 2 material. So those are non-ideal phenomenon, and we will not discuss them, but just as key points, I wanted to mention that once you introduce different gates, so you will be having the problem of distributed work functions for different materials, and you can also have the problem of the grain boundaries in the different materials, which can cause changes in the current density profiles along your fin. So these are the key points in understanding the simple classifications of these FinFETs. So again, I have collected a few interesting facts about FinFETs, and these are far interesting than what we have done till now, because this speaks of the current year 2020. The 2020 IEEE Medal of Honor Award has been given to Chen-Ming Hu for his invention or for his fabrication of the FinFETs. And he has been termed the father of FinFETs because of this distinguished contribution to the semiconductor industry. And while delving deep into the development of these FinFETs, he also founded the BSIM models, which you encounter in your SPICE simulators or your current simulations, or your circuit simulations. And it is said that Chen-Ming Hu sketched the first designs of the FinFET on a flight ride to Japan. So this is quite like a humorous fact, which has been put up in the IEEE Spectrum, published on 21 April 2020. And the FinFET is actually the result of a sponsored project by DARPA, the Defense Advanced Research Projects Agency of the USA. And it is said that the problems started appearing for MOSFETs. So this is quite related to what we are discussing here today. So when the MOSFETs were shrunk in order to meet the Moore's law, and when it was found that reducing the dimensions below 100 nanometers were causing very trouble to the researchers and the engineers, so then DARPA tried to lease out a project call for the 25 nanometer switch. So DARPA called it the 25 nanometer switch because they wanted to go far below the actual limit which they were facing. And Chen-Ming Hu was the first one who took up this project because he liked the term 25 nanometer switch. And then he went on to develop what you find today in your mobile phones and different processors, the FinFETs. And this is just an add-on for Chen-Ming Hu. Most of you must have come across his research papers. They are very interesting, particularly the ones on hot electron effects. And also, Hu's books are also available for taking up in postgraduate and undergraduate studies on MOSFETs. And Hu's first job was a tutor. He was a tutor for high school students, and later he became assistant professor at MIT. And currently he's the TSMC Distinguished Professor Emeritus, University of California, Berkeley. So these are some of the facts which I could gather about FinFETs, which are very much relevant. And if you look into the reference which I have put up on at the bottom of this slide, you can read the entire article and find out how interesting it is. So next, let us look into a few characteristics of FinFETs. So this was one of the work which we tried to do in the initial phases in around 2016. And this work, basically, it compares some of the modifications in architecture. So I consider it to be a very raw work because after that, many developments have come for FinFETs. But this work is interesting because it gives you progressive developments on the basic architecture of FinFET. And as you can see, this structure which you see, the various abbreviations are laid out. the single gate material, single dielectric, heterojunction FinFET, and the dual gate material, dual dielectric, heterojunction FinFET. So what we tried to do, we took up a normal FinFET, a conventional FinFET, and went on adding up or modifying the different architectures which have been done for MOSFETs. And we selected a heterojunction just to see the effects. We selected this germanium, and we put up silicon in between near one of the junctions, and then we tried to evaluate the performance. So you can see the characteristics on this screen in figure 4.6. In figure 4.6a stands the different transfer characteristics for the 4 architectures. So the black one, which you see for the conventional FinFET, has very high leakage current, high off-state currents, but also it has high on currents. But as soon as we are adding up more layers, or say more dielectric materials and work functions, the off-state current decreases, and the on decreases by an order of around 2, and the on-state current decreases by an order of 1, which is again very consistent with the ITRS requirement at that time. So this, you can say, is basically a very basic study on FinFETs on the different architectures. And in 4.6b, you can see the impact of the fin width of the FinFET on the transfer characteristics or the drain current. And an explanation has been provided in figure 4.6c. So you can see for the 10 nanometer fin width in figure B, the current is higher in and around the mid gate voltages of around 0.4 to 1 volt. So it is higher for 10 nanometers fin width than 16 or 18 nanometers, because for 10 nanometer fin width, you can have a better control of the gates because the fin width has decreased. So you can control any point or any position in the fin, inside the fin or in the channel from all the 3 sides. So this was one of the analysis which we had completed. And the idea of putting this here is just to give you a basic idea of the characteristics of FinFETs. And you can see the leakage current is very lower than MOSFETs. MOSFETs, if they would have been done at this same lengths. Next, we are moving into the memristors, another emerging devices, or you can say these are application-specific devices. They are normally used for neuromorphic computing and neural networks, in realizing neural networks. So the story behind this is again more interesting, but before that, let's see what these memristors are. So you know that there are 4 very basic electrical quantities: the voltage, current, flux, and charge. And each of them are related, and they give you a parameter depending upon the relationship between them. So for example, this resistance is given as a relationship between your voltage and current, right? And similarly, you can have the capacitance as a relationship between the charge and the voltage, and the inductance as a relationship between the flux and the current. But you do not find actually any relationship between your flux and charge. So intuitively, there must have been a particular electrical parameter which relates these 2 quantities, and so that the entire circle of these quantities are complete. So actually, this missing relation is nothing but your memristor, and the symbol for memristor is square type of waveform connected to 2 terminals. So it gives you the relationship between charge and flux, the basic relationship, and this completes the entire circle of these 4 electrical parameters. Now, one question which appears here is that what was this memristor doing during all this time? Why people had not tried to see this missing link? So the answer to this is the link between this charge and flux was reported by Leon Chua in 1970s, theoretically. So he first proposed that there must be an electrical parameter in nature which can link these two quantities. So that was the first instance of the official report of the memristive action as a whole. Okay, and this interesting fact is that you have in 1971, Leon Chua was a senior member IEEE at that time. He gave the theoretical description of the memristors. In 1976, he and his student Kang, they extended this particular concept to devices and systems. And after that, interestingly, you did not find anywhere the realization of this concept of memristor until 2008, when Hewlett Packard, also better known as HP, fabricated the first nanoscale memristor using titanium oxide. So this is the entire layout, and if you see, it is quite interesting that someone had come up with a theoretical version of an element which would prove to be one of the biggest inventions in future, and that also after 37 years. So this is how we are going through the different phases of research. So until 2008, no one had discussed about the theoretical description of memristors widely, because everyone was confused about this switching phenomenon. So basically the memristor acts as a switch. It has a dual state and it has a hysteresis in its IV, which we will see in one of the upcoming slides. But only in 2008, the HP labs, they first reported the first nanoscale memristors. And since then, it has caught the semiconductor industry just like a storm, and people are just doing research on these memristive elements and the different circuit architectures, and it has gone far than expected in a very short time. So as I have said, the memristor in 1971 was the first official report by Al Chua. But later, Chua realized that even before 1972 and even after 1972 up to 2008, there were instances of experiments in which similar switching phenomena or memristive action was found, but no one called it a memristor or linked it to Chua's concept of that missing link between flux and charge. So this is the idea, that whenever you are doing an experiment, or say you are going through an analysis, you will find there are multiple number of parameters, and some of the parameters we just discard because they do not seem appropriate at that particular moment. But you can see, if you find that that is a rare and a very accurate phenomenon going on somewhere, so you just need to report it somewhere in your article, so that you have the advantage of at least putting it out to the world for discussion. So that is one of the objectives of why I have put this point on this slide. So these are some of the characteristics, and one of the very basic requirement of whether a device is a memristor or whether a system is memristive in nature is it must have a pinched hysteresis in its current voltage plot. So please listen that it must be a pinched hysteresis. So every one of us know about the hysteresis plot. We have encountered this in electromagnetics and many other devices and systems, but it must be pinched. So it must look somewhat like the letter 8, so that it is pinched somewhere in the middle. So as you can see, both these curves or the characteristics are pinched at the origin. So at voltage and current of 0, 0, it is pinched, and after that it goes into the different two states of that particular curve. So on the left hand side, what you see was fabricated by Johnson et al. In 2010, and on the right hand side you see the first realized the characteristics of the first realized memristor by HP. So the persons who represented HP were Struikov and Snyder, and these are the characteristics, and you can see that there are two states for a single voltage. Say for example, I am picking up 0.5 volt, I can see two values of current for the same voltage, one while sweeping it upwards and one while coming downwards. So you can see it has dual states, and these dual states can be exploited for any digital logic or any neuromorphic computing. So this can also, you can think in the very basic sense, you can think this of something like 0 and 1 in digital circuits or in digital logic system. So one resistance or one single current value which is lower can correspond to a 0 logic value of 0, and the other one with a higher current can represent a logic value of 1. So these are examples of the characteristics, and we will discuss a specific and a very interesting application of memristor in the next section. So the upcoming section, I wanted to take this up because it is very trending, the biosensing applications. And we have been working on some biosensing applications using TFETs and memristors. And these are quite interesting, particularly in the case for memristors, where we discovered a very interesting property of protein containing food items. So we will discuss these points. So the first one, using tunnel FETs, we will try to see how it gets implemented as a biosensor. So here you can see there are actually different types of biosensors. There are wet sensors and there are dry sensors. And wet sensors are usually easier to fabricate in laboratories because you just need a bionic solution, and you need a suspended gate electrode or a fixed gate electrode to sense that particular molecule. But that is not what we are going to discuss. That is also known as the ISFET, the ion sensing field effect transistor. So here we will be discussing a rather very close concept, a concept which is closer to the operation of TFETs and not more towards the biomolecules, although we are discussing biosensors. So you will be able to relate the operation of this entire device of this topic so that it can be widely received. So what you see in dielectric modulated, as the term suggests, the gate dielectric is etched out in one of the portions, and in that particular nano gap, which we can call, we can incorporate the biomolecules. So now this work was entirely done on simulation, and we obviously used calibrated simulation, and the values which we took for charge values for the different biomolecules and the dielectric constants were picked up from different sources, valid sources, which actually corresponded to those dielectric constants and those charges. So we took up two devices. First of all, the circular gate tunnel field effect transistor, which you just saw a couple of minutes earlier in the section for TFETs. And another one is the heterojunction TFET, which is again, which you have encountered a couple of minutes earlier. So we, as you can see, we have etched out a nano gap, and then we are trying to incorporate the biomolecules. But there are a few things here which you need to understand. First of all, the 1 nanometer of yellow color which you see is your SiO2. So this is the sacrificial layer, which is called, which often comes into account while the processes. So therefore we have taken that, and we have considered a fixed dielectric constant of 10 towards the drain side, which you can see as this shaded portion here. So this is a fixed dielectric material here, and this is empty, and this red just signifies or symbolizes the biomolecules. And then we tried to go for the sensitivity for both the devices. And here I only show the negative charge of biomolecules because biomolecules they will on top of this SiO2 layer, you will have to put some material or binding layer to connect to these biomolecules in a sense. The charge is then transferred from this biomolecule to this binding layer, and then the different actions or the implications on the drain current are observed. So therefore, discharge is one of the most important part of understanding DMT-FETs, the dielectric modulated sensors. Also, this magnitude of this negative charge is motivated by the charge of a DNA. So of a negative DNA strand. So we have taken that value, from one of the works by Rakhi Narang and Manoj Saxena. And from there, we have tried to just vary the ranges and see how the sensitivity varies. And the expression for sensitivity is given here. So we have taken the air as a reference. So it means first I will check the drain current of these devices when this nano gap is empty or is filled with vacuum or air. So which means I will measure this at a dielectric constant of 1, which is the permittivity for free space. After that, I will try to put the biomolecules and then again measure the current and then take this ratio and express it as a sensitivity. So in figure 6.2c, you can see that MOSFETs, the comparison of both the TFETs in comparison to MOSFETs. So both these TFETs have very higher sensitivity as compared to MOSFETs. So this gives an indication that these TFETs can be very popularly widely used for this dry kind of sensing. But there is a limitation here. The limitation being, if you are thinking of implantable sensors, so then you have to go with something like more with a wet kind of sensor, because once you implant it to your body, so you will be having the different fluids, the ionic fluids. And also another thing, you'll have to be very selective about your binding layer, because you will be penetrating it into the human body. So it must be biodegradable and non-toxic. So therefore, you see many researches coming up on biodegradable semiconductors or materials or insulating materials. So this is one limitation. You cannot use the dielectric modulated TFETs with dry sensing because ideally you will not find a dry environment inside your human body. And therefore, these are mainly targeted for pharmaceutical applications in laboratories, where you can put them in a confined environment and then check the response to different biomolecules. So another case, so till now, these graphs which you see on your screen for sensitivity, these are at 100% fill factor. It means we have assumed that the entire nano gap is filled with the biomolecules. But in reality, you may not be having that picture. So we have taken 4 different profiles, the concave, increasing, decreasing, and convex, and tried to vary the fill factor and see the changes. So you will find that the sensitivity is higher for your decreasing profile and your concave profile. So the reason for this is obvious. So once you just look at this concave profile here, you will find that the height of this step which we have taken up, of this partial hybridized step here, of this hybridized biomolecule step, is higher as compared to the rest. So if you compare this concave profile and decreasing profile, you will find near the tunnel junction, you will be having a higher width or a higher thickness of this biomolecule step, as a result of which you can induce here more gate control near the tunnel junction. So you will get higher drain current for this particular dielectric constant. So you see this top very rising bars here for decreasing and concave profiles. Now take for example this increasing profile. So you will see that towards the left hand side or towards this junction, I have a very smaller step. So which means in this particular case, air will be the dominant dielectric material here. So air has a very lesser dielectric constant. So as a result of which you will be having lower currents. So same reason goes for convex. So it is related to the arrangement of this biomolecule steps for these different profiles. And we have concluded that if your biomolecules are lying towards the tunnel junction, are lying more towards the tunnel junction with a higher step height, so in that case, your sensitivities will be higher. Finally, we have this another non-ideal effect on probe placement. So remember, I have talked about that binding layer. So usually you do not have a uniform binding layer all the time throughout the length of your particular device through the cavity. So there it may be the case that in some cases the probes are placed well, and in some cases the regions are empty and there are no binding layers. So therefore, what we have done in this, you see in this second column, where we have mentioned this nano gap of as 25 nanometers, we have divided it into 10 different parts, and the shaded parts are the ones which are covered by the binding layer, and these parts, the empty parts or the white blocks which you see, are not covered by the binding layer. So if there is a binding layer, only in that case there will be a biomolecule which can be hybridized. If there is no binding layer, so we have assumed that there is no biomolecule for that particular region. So total length of nanogap is 25 nanometers, and 10 divisions make each of them as 2.5 nanometers of length. So you will see that if we are having more biomolecules again towards the tunnel junction, so on the left hand side is your tunnel junction, and on the right hand side is your channel drain junction. So we are interested towards the left hand side. So you will see as we increase the number of black blocks, continuous black blocks in your particular device, you will see that the sensitivity will increase as compared to the others. And also, just look at the last three cases, case 7, 8, and 9. You will find there are empty blocks just at the tunnel junction. And in that case, you will find that the sensitivities are very low, and in some cases, they are not even measurable. So therefore, I have put there as nil. So you can see that since TFETs, in TFETs, the tunnel junction is the most important area. So it is a challenge to concentrate most of the activities around that particular junction. Okay, so this is an advantage in the case that the channel can be shrunk down, but also it is a disadvantage because you have to be very careful about the source doping concentrations and the tunneling width in that particular region, and you have to be very careful about the steepness of the profiles in your junction. So everything comes with a boon as well as a bane. So that is the case for TFETs. Next, we'll move onto memristors, the last topic of this webinar. And this, as I have already said, I have kept it at the end because it is going to be very interesting. So what we did, this was entirely our idea of conducting an experiment on food items. So till date, as I have said, many memristors have been realized, and many memristors have also been realized using silk proteins and also using chicken egg albumin. So albumin is a very rich protein source, and using that also people have fabricated biodegradable memristors. But we tried to go on a macroscopic scale rather than going into the nanoscale dimension. And we just tried, the motivation we got was if we could build a food protein sensor, because proteins are very important consumption item for the healthcare sector. So if we can build something out of food proteins to sense the things and get it out to the consumer level or at least the industry level, so it would be a very good. I tried to develop this sensing area using normal plastic container. It should be an insulator, otherwise you cannot have the contacts placed very well. And we use these electrodes to hold the sensing area. And we used a very simple potential divider method so that we don't have much problem in arranging the setup, because readings were very much important than the setup in this particular experiment. And we used a function generator to generate an AC waveform or a time varying waveform, because memristors, if you want to see the hysteresis, a time varying waveform is required because you need to sweep up and sweep down particular voltage points So therefore, we connected one end of the sample to the function generator and the other end to the oscilloscope. Also, another point which I need to mention here, the frequency of the supply signal must be very low. So it operates in the range of 25 to 50 hertz, because at higher frequencies, the memristive behavior will disappear. So it will become a straight line. There will be no hysteresis, even if it is a memristive material. So one of the other conditions is that you need to operate your memristive devices, or if you want to check whether a device is memristive or not, you need to operate at a lower frequencies. And that is a huge challenge if you are trying to develop a system on chip, because creating great challenge in system on chip. So first of all, to be very confident of what we are doing, we took chicken egg albumin only. We filtered out the yolk portion, and we tried to check the memristive behavior first by first placing that albumin in that sensor holder and then checking the waveforms. And after that, we denatured it. So denaturation is the process by which you can filter out the proteins from your materials. So we filtered out the proteins, and after denaturation, we found that when all the protein was gone, we found straight lines. So you can have a hysteresis only when your waveform, your time varying waveform has different voltage points at different instance of time. So in the figure 7.2a, you can see, say for example, I take up an increasing part of my slope here. So it will have a different voltage, and at the same voltage here of the supply signal, I'll be having a different voltage. But once I filter out the protein content from the albumin, I will find that they give a pretty straight lines and linear curves. So we were pretty much confident that we can proceed with the experiment with proteins. And these are the characteristics. I am not showing the entire set of curves here because it is under the process of a patent. So I am showing only selective portions of the curve. So you can see the hysteresis here. We used a triangular waveform. So therefore, you do not see the perfect letter 8. Rather, you see piecewise 8 kind of structure. And you can see as we increase our concentration, the hysteresis bends towards the right-hand side, which means its slope decreases. The slope of this current voltage characteristics decreases. So that is one very important metric through which you can characterize this entire sensor. And these are two individual curves which are present for 103.30 milligram per milliliter concentration and 32 milligram per milliliter concentration. And you can see for the one with higher concentration, the curve, the blue line which you see is the voltage line, which the voltage plot across the sensing sample, and it is very non-linear as compared to the blue line here, which is for a lower concentration. So you can conclude or say that if a substance is memristive, it will show a very highly non-linear behavior at lower frequencies. And if it is not memristive, so it will show a linear waveform versus time. So this is one of the developments which I wanted to share with you all because this is quite interesting and a very good point to start with macroscopic memristors. So I thank every one of you for just being patient and listening to this webinar. So we can see here what we can do from this point onward, what we can do as a researcher or as a student. So you can see that the research on emerging devices is necessary to support the demands of the industry. But the question is, should we continue to focus on downscaling our transistors? Because you are downscaling a transistor because you want to put more functionalities per chip. So therefore, your older mobile phone versions did not have these high pixel cameras as compared to the ones now, which are embedded in the same area. So they are occupying the same area with higher functionalities. So you are putting more transistors means you are putting more functionalities per chip. So the question is, should we always or blindly scale down our devices, or is this the right time to select a device based on the requirement of the functionality? So this is one question which we can explore, and it can lead to a very wonderful research statement. Secondly, atomic level analysis are necessary for prospective future in devices. So the times are gone when we just started with the Poisson equation and went down to the drain current. They are relevant even today, but now it is the high time to include different quantum mechanisms in your models, just like your quantization and the different band-to-band tunneling models, and also the different Poole-Franken dropping effects. And for these are also need to be taken up in your models. And in line with this, the question again, is Poisson equation sufficient for modeling? So it may be sufficient for some devices, but it may be very difficult when you are scaling down the devices and taking up more novel devices. Also, the calibration of experimental devices is very necessary. So if you are doing a simulation, first of all, you pick up an experimental device having closest material to your simulated device, and then try to calibrate all the constants on your simulation tool. Only after that, you move into the simulation analysis. And finally, the most important one is that device circuit simulations must be integrated, and very less research is done at this particular point in device circuit simulation integration. Okay, so I think I know that I have not been able to cover the entire concepts and everything related to these devices, but I think I am able to get out to you on some of the key points related to the topic of this webinar. So these are few acknowledgements to my teachers and colleagues, my students who have been working on different topics which I have presented, and the funding agency which is sponsoring. So thank you, and I'm ready to take up a few questions. So I'm ending this webinar at this note and taking up the questions which I receive from the coordinator.
Some questions has the questions posted in the chat section in the Google Meet has been WhatsApp to you.
Yes,
Please
yes,
check
yes.
it.
Yes, yes. So just give me 2 minutes. Okay, I am taking up a question related to the. So a question was, the root part in the. Am I audible?
Yes.
Yes.
Okay. Yeah. So this 2 which you see in the WKB approximation actually comes because when you take the limits, when you usually set the limits from 0 to B, instead of taking from -B to plus b or something. So we are just counting this on both sides of the integral by including this 2 in the expression. So I'm taking up another question. Please explain how memristors are fabricated and its applications. Okay, so this question is put up by Nimit Jain. The earlier question was by Shruti Chauhan. So, Mr. Jain, I would like to say that the entire fabrication of memristors, it's not possible to take up at this moment, but I can tell you the brief points. The fabrication of memristors is very simple as compared to your MOSFETs or other semiconductor devices. Since I am more inclined towards biomemristors, so I can comfortably comment on the biodegradable memristors. So for example, for the biomemristors, you need to understand that it is a two-terminal element. The memristor is usually a two-terminal element. So in most of the articles or the reports which have been done by experimentalists or researchers, so they have extracted that biodegradable material in the form of a fluid, and they have filtered out the different macro constituents of the fluid and then spin coated it into that particular substrate. Either it be a flexible substrate or say an insulating substrate, and using that the memristor was realized. So usually it is a very simple fabrication method, and you can also see from the last section where I discussed, it is very simple when you see it on a macroscopic level. So that also, if at a macroscopic level, any particular material when connected as a two-terminal element can give you a memoristic property. So you can imagine that even if we scale down the dimensions, the fabrication process still remains very convenient as compared to MOSFETs and other devices. Another question by Shruti Chauhan. How can the temperature be varied in TCAD tools to make it useful for thermosensing? Okay, this is quite an interesting question. First of all, Ms. Chauhan, it depends on the TCAD tool you are using. So I have basically worked on the center TCAD tool. So I'm commenting my answer with respect to that. So basically, whenever we are doing temperature analysis for a device on a TCAD tool, we try, first of all, to vary the ambient temperature of the device or the lattice temperature, which is very more specific. Secondly, you need to tune your models with respect to those temperatures, because most of the experiments are based on fabrications done at room temperature. So you need to get hold of an experimental device which can give you a calibrated curve for a lower temperature or a higher temperature than room temperature. It is very intuitive that you select the parameters you have calibrated at room temperature and then go on with the rest of your simulation. But I would recommend that you do not blindly take up the values for room temperature and apply it to other temperatures because there may be many other phenomena related to that. Okay, so hope this answers your question. And secondly, Ms. Chauhan, there is another question. Can't SiO2 be etched entirely from the cavity? Probably this is with relation to biosensors. If it is necessary, then what is its thickness? So actually, you cannot, there is a very greater risk of damaging the surface of your semiconductor if you are trying to etch out the entire silicon dioxide. So therefore, usually it develops and it is kept as such as a sacrificial layer, and it has ranges in angstroms up to 1 nanometer. So therefore, we have taken it as a value of 1 nanometer in our simulations. So this was already reported in experiments that the sacrificial layer is. So we have particular. There is another question by Dr. Raghavendra. What is analogy for memristor? So I am not so clear about the question. So I will expect a bit more light on the question. I'm not able to get it what he means by analogy. So I'm skipping this question as of now, but I'd love to get back on this. And
you can take few more questions, and the rest
yeah,
of the questions and the answers will be provided in the email.
Yeah.
Or even in the WhatsApp group also.
Yes. So there is another question by Nisar Gajjar. What are the present and future industrial applications? So, Mr. Gajjar, there for FinFETs, you are currently in an era where FinFETs are the most viable and potentially exploited devices. So in future, if you are trying to work on FinFETs, so you can look out for tunnel FinFETs, which means you make a FinFET out of a tunnel FET, or if you apply the same fin shape structure to a ferroelectric field effect transistor. So you will, I believe, you will find some very exciting results. People are starting to work on such kind of devices. So they are just combining the advantages of FinFETs and TFETs. So I hope I'm able to get out to you on this point. And another question by Avishek Singh: what are the factors affecting current? How can we reduce it? So as we have already discussed in the TFETs, the factors affecting ambipolar current, the first one is your drain doping concentration. So if your drain doping concentration is very high, so the tunnel junction and the channel drain junction will be very steep, and as a result of which it will lead to more ambipolar current. So first of all, you need to optimize your drain concentration. So usually what we do, we take the source doping concentration at 10 to the power 20, and for the drain doping, we keep it at 5 into 10 to the power 18 or 10 to the power 19 inch, so that we have reduced ambipolar current. Another way is to introduce the gate drain underlap, which we have discussed, and these are the things, these are the factors which you can use these are the solutions which you can ambipolar currents reduce. There is another question. Dr. Manoj Circular Farida, how TFET is better than other TFET? Okay. So Dr. Parida, the circular gate TFET, I just mentioned the advantages. So you can see the circular nature. So if you look at the circular nature of gate here, you will see towards the source channel junction, the tunnel junction is lesser dielectric thickness. And as you towards the drain junction, you can change the gate drain underlap as well as the dielectric thickness at the same time by changing the radius. So this will give you a current as well as a very low ambipolar current. Okay, and I'll take up the last question. Why are memristors not applicable to computer storage by Vishal Goswami? No, memristors are actually they are implemented as resistives. So they are, I think, very much applicable to computer storage. I don't know if that is viable or commercially available, but researchers are being put on implementing them as resistive random access memory. So that is the case. So I think I will end taking up questions. I'll take up the rest of the questions through the WhatsApp group. I hope that is okay, Dr. and Dr. Saha.
Yes, absolutely.
Okay, so
yeah. So thank you, Dr. Rupam Goswami.
Thank you, everyone. I thank.
Okay, thank you, Dr. Rupam Goswami, for this wonderful talk. And now I would request Professor Rajni Vishd ma'am to conclude the session. Professor Rajni Vishnu.
Thank you, Partha. Now on thanks to Honorable Vice Chancellor L.B. Singh, who has given his blessing speech on the inauguration function of this webinar. I also thank the speaker, Rupam Goswami, for giving such an knowledgeable speech. Like Vice Chancellor sir told that we should interact with researchers for the webinar. So actually, instantaneously, he did the task completed. This was very nice talk to hear in the webinar on the emergent devices. I also thank Professor Krishna Raj, Head Electronics Engineering at VTU Kanpur, for organizing, as he was a key person for organizing such a good seminar, which is helpful for students, faculty, and researchers. Like I've seen so many, more than 150 plus people are hearing this webinar. I also thank the participants and mostly I also thank to the coordinator, Dr. Suman Mitra, for arranging such a nice webinar, and Dr. Partha Saha for conducting the seminar. And I'll see in future. I hope that they will be doing such seminars again, webinars again. Sorry. So again I'll thank Dr. Rupam Goswami for such a nice seminar and giving with the historical perspective. And one point I like to share that he told for the future scope that device and circuit simulations are to be integrated. This is very hot topic, or I should say this is a demand of the time, that otherwise device workers are working separately and circuit workers, researchers are working separately. So tools as well as the team should also be integrated. Then only the viable solution for the future prospects can be bring out with this with the research. So thank you very much to all the participants, and congratulations to the team workers, to Head Electronics Engineering for such a nice webinar, and to the coordinator, Dr. Suman Mitra, and Partha Saha, and the other NPIU team who are working for this. Thank you. Thank you very much.
Thank you, madam.
Thank you, sir.
Thank you, madam.
Thank you.
I would request Dr. Suman Mitra to give the link for the feedback form in the chat box. I think it is there in the chat box. So I request all the participants to please fill the feedback form so that we can improve our next webinar depending on your comments. So you can give the feedback, and I think the link is also provided in the WhatsApp group also. So you can go there and give the feedback. Finally, I would like to thank all the participants for being with us in this wonderful session and the talk given by Dr. Rupam Goswami. So I would like to thank all the participants for joining with us. Thank you.
Thank you.
Thank you.
Thank you, sir.
Thank you. Thank you.
Thank you. Thank you, sir.
Thank you. Thank you, Rupamji.
Thank you, sir. Thank you, sir. It was a
Thank you.
pleasure.
Thank you, Rupamji.
Thank you, ma'am.
Thank you, Rupam, sir, for a very
Thank
nice
you.
talk.
Thank you.
Okay, thank you. Thanks to all organizers, thanks to all respected faculty members, and thanks to all respected audience for supporting us and motivating us. Thanks.
Thank you, sir.
One and all.
Thank you.
Thank you.